Welcome to our next lecture and lecture series Climate Protection. And in the very beginning, I want to ask the audience, in the virtual audience, if there are any technical problems with, can you hear me? Is there an echo or is fine?
Yes, we can hear you.
Okay, thank you. Okay. If there are any technical problems, please say it or write it in the chat that we can see and try to fix it. But it looks that it's work. Welcome to the second lesson in the lecture series Climate Protection in summer semester 2022. In the very beginning, I want to take a spotlight on the climate strike. It's pretty important for everybody to have be there, or hopefully you want to go there after the lectures. It should be in every city. Today it's a global climate work strike. To raise your voice for this topic, it's pretty important. And today, I'm really glad about that Ulrike Lohmann is here and will have a speak, a talk, and discuss with us together about a really pretty certain topic. Ulrike Lohmann is a full professor of the experimental atmospheric physics in the Institute for Atmospheric and Climate Science since October 2004 in the ETH Zurich. She was born in 1966 in Berlin, Germany, and studied from 88 to 93 meteorology at the University of Mainz and Hamburg. In 1996, she obtained her PhD in climate modeling from the Max Planck Institute for Meteorology. Prior to her current appointment, she was a postdoctoral fellow at the Canadian Centre for Climate Modeling and Analysis in Victoria, and an assistant and associated professor at Dalhousie University in Halifax. It's located southeast Canada, next to Maine in USA. She was awarded a Canada Research in Chair in 2002, received the AMS Henry G. Houghton Award in 2007. She was elected as a fellow of the American Geophysical Union in 2008 and of the German National Academy of Science Leopoldina in 2013. Ulrike Lohmann has published almost 300 peer-reviewed articles. She was a lead author for the 4th and 5th assessment report of the IPCC panel. She was the coordinator of the EU FP7 project Bacchus 2014 to 18, and chaired the Eichmann-Amos Consortium 2009 to 17. At ETH, she was the head of the Institute for Atmospheric and Climate Science from 2006 to 2014, is a delegate of the ETH president for heading search committees and president of the lecture conference. She won the Golden Tricycle Award for family-friendly supervisors from ETH Zurich in 2013. Became an honorary doctor of Stockholm University in 2018 and won an ERC Advanced Grant in 2021. Since 2018, she is one of the SNF Research Commission. Now I am glad that Professor Ulrike Lohmann is today here at the lecture series Climate Protection to discuss with us together about the topic Geoengineering. Is this a way out of the climate crisis? Welcome, Professor Lohmann. I want to give you now the reps.
Yeah, thanks a lot for the introduction. So far, I cannot. You have the control of this. What? Oh, I can. Good. Okay, so yes, geoengineering way out of the climate crisis. Why is this of interest? I picked here examples of extreme events in summer 2018. What is this? Share. Okay, that's better. The echo still remains though, so if you can unmute everything you have, that would probably help me. Now it's better, thanks. Okay, so climate crisis. Why are we talking about this? Well, there's different ways on how we can look at this. So examples here from 2018 were a very dry summer. So you see that on the one hand, you have too little precipitation because the river beds are dry. And on the other hand, there's flooding of the whole subway system here. So if the rain comes, then it comes too intense at once. No, I cannot. Can I advance? Okay, perfect. On the other hand, it was not only Switzerland, it was just the examples that I picked. 2018 was also the summer where there were forest fires in Sweden. In California, as you see below, that happens more often, but that you have forest fires that far north was really unheard of. And the record temperatures in that summer were such that episodic storytelling said that the reindeers were seeking shelter in the underground tunnels just to have a place where it's not too hot to them. So definitely climate is changing. Well, if we look at this, our source of knowledge that we have are the so-called IPCC reports, Intergovernmental Panel on Climate Change, of which the 6th report was just released last year. And all the time, if you look at the reports, you do see how the temperature has changed since pre-industrial times. So if we start here from, let's see if I can change, if you can see my mouse, but I'm not sure. Maybe, I don't know how this works here in this setup. Okay, I'll do it like this. So here you see the temperature change with respect to the reference period. And you see that if you had a simulation, climate model simulations, where we only included natural forcings, changes in solar radiation, and changes in volcanic eruption, you see that the temperature would remain around 0. So that's anomalies from the global mean. So there's no trend. You only get a trend once you superimpose all the anthropogenic forcing, so our greenhouse gases increases and aerosol increases. And now IPCC uses mathematical statistical methods to tell this apart, to say how likely is this that we see such a warming without us humans doing anything. And the answer is 98% of all the warming that we have seen from this period until today, so that's a total warming of almost 1.1 degrees, 98% for that is due to our doing, is human induced. So it's clearly us causing the problem. But I guess you know that, especially if you're going to the climate strike. Then the question is, what are the sources? The very dominant sources of all is here our well-mixed greenhouse gases. First of all, carbon dioxide contributing alone to a warming of 1 degree. So we have seen a total was 1.1 degrees, and 1 degree out of that is just due to carbon dioxide. The minute we add the other well-mixed greenhouse gases in addition to that, we get an additional warming of around 0.7, 0.8. So if we just take greenhouse gases, then the warming that we have seen would be even much larger. So there is something that works against this warming, and those are so-called aerosol particles, so tiny particles in the air that reflect sunlight, and with the sunlight, with the reflected sunlight, less is absorbed at the surface. At the same time, they also perturb cloud properties. And so they make the clouds brighter, and because they make the clouds brighter, even less radiation reaches the surface. And that caused a cooling of approximately half a degree. And this is when we are discussing now geoengineering or climate intervention or whatever you want to name it. This is what people think about just because we know that there's a cooling and some of the mechanisms we do understand. But before I go there, let's see what's going to happen in the future. This is from the 5th IPCC report. It has been updated as well, so it will change slightly, but the message is the same, that it depends upon if we take vigorous measures to stabilize the warming, or if we continue with a business as usual scenario. And if we do that, we could have a warming of 4 degrees higher than pre-industrial by 2100. Now, in 2015, there was the Paris Agreement, and the Paris Agreement says that we should keep the temperature increase well below 2 degrees above pre-industrial levels and try everything to limit the temperature increase to 1.5 degree above pre-industrial. I started out by saying that we already have 1.1 degree warming, so it's not a lot of warming that's left. Where is this 1.5 or 2 degree come from? Is this a magic number? No, it's not. But it is something, and I will show you that in the next slide, that the climate system has different components, and different components can withstand a larger warming or less of a warming. So, but if we look here, there was a special report coming out again from IPCC, what it takes to keep the warming below this 1.5 degrees. So special report 1.5 degrees is what this means. And you see that at the time this was published in 2018, it says, okay, if you continue with the current warming rate, then we reach 1.5 degrees by 2040. So it's not a lot of time that we have left. This is what in IPCC it's called an amber diagram, just from the color coding of some of the impacts that we see. And so this here is the temperature range, the warming, the 1 point, or in this case it was 0.8 to 1 degree warming above pre-industrial, and the impact it has. So to read it, as long as everything is in the white color, it's fine. So for instance, mangroves are still fine with the warming that we have. There is some moderate impact already, say if you look here at fluvial flooding, coastal flooding is already going towards the red for current, at current conditions. And you see here in the Arctic region, the red is even reached even faster. Small scale, low latitude fisheries. Fisheries have a problem already because the fish cannot live in the warmer waters. And the ecosystem that suffers the most and suffers already nowadays are warm water corals. So because of that, what you see here, there's not just one threshold, say above 1.5 degree, everything is going to tip, so-called tipping points. The warmer it gets, yes, the more changes there are that you cannot revert. For instance, once the Arctic sea ice is completely gone, it's much, much harder, or glaciers. So once they are completely gone, it takes forever to rebuild them. So this is what is sometimes referred to as tipping points, and that's why we want to keep the warming very much below 1.5 degree, if at all possible. What does it take? Well, if you conceptualize that and look here at climate damage on the y-axis and time, then if we continue with business as usual, what we just saw from this amber diagram, the impacts will be more and more negative. So we know that it takes huge amount of reductions in CO2 emission. This is what it really takes. But this is a slow process. It hasn't started yet, not significantly started yet. So we need to get there, but it will be a while. At the same time, there is research being done at trying to come to so-called negative emissions. So this means removing CO2 from the atmosphere. But that technology is also not too well established yet, and it takes time to implement. So the thinking behind what's sometimes called geoengineering or climate intervention is to avoid this part here of the climate damage and cool the climate system in the as long as it takes for the temperatures to go down. And that's what I'll be talking about. We see one slide to the negative emissions. If you look here at all the representative concentration pathways between where we are now and in the year 2100, then you see, for instance, if you want to keep moderate warming, so here this one, the RCP 2.6, would be the one that is in line with the Paris Agreement, then you see that it already assumes that at one point we are able to have negative emissions technologies, so i.e. are able to withdraw CO2 from the atmosphere. And even in this pathway, some of this is being factored in. So this is already assumed, and what I'll be talking about is can we avoid some of this overshooting that is here to come. Okay, I have shown you that aerosols cool the climate, and aerosols cool the climate more if they change cloud properties. So the question we are asking ourselves is then, which clouds should we target? Should we target highly convective clouds, thunderstorms? The answer is no. They are so short-lived, they are so vigorous systems that wouldn't work. They don't have a large vertical, horizontal extent. So if we want to perturb clouds, it should be clouds that have a large horizontal coverage. Something like this, obviously not in winter, because in winter you don't have less sunlight, but a stratospheric would be a good cloud that you could target. Also here, cirrus clouds may also be of interest, because cirrus clouds act similar as greenhouse gases, so they also warm the climate system. So I'll go more into that in a bit, but the general idea would be to make those low-level clouds more reflective and or try to get rid of all the cirrus clouds that we have. So the opposite of contrails. Instead of producing contrails, we want to make sure that we never ever produce one, and in addition reduce the natural zone. Okay, but to explain this a little more, what is the role of clouds in the climate system? If you look here at an energy diagram, global annual mean, average, we receive on average we receive 340 watts per meter square. Of this incoming solar radiation, half of that goes to the surface, and roughly a third of it is reflected. Of the third that is reflected, 3/4 are reflected by clouds, aerosols, and gases. And here, the most important is clouds. Roughly 2/3 of this, little less than 50 watts per meter square, are reflected by clouds. So if you think of that, a greenhouse gas, a doubling of CO2 is approximately 4 watts per meter square. This would correspond to increasing the coverage of low-level clouds by around 10%, and then you would have offset a doubling of CO2. On the other hand, here we have our high-level cirrus clouds that act similar to greenhouse gases, and what they are doing is they absorb the radiation that's being emitted from the Earth or the atmosphere below them, and they form at the very coldest temperature, so say at a temperature of -60 degrees, and they emit very little radiation back to space. And so they trap the heating within the Earth atmosphere system. So if we were able to get rid of them, more radiation would escape, and that would lead to a cooling. So what we can also look at, or what is worth looking at, how are clouds changing with climate change? Maybe they help us naturally. Unfortunately not. What has been observed that the high clouds rise even higher. And important for how much radiation they keep in the system is the difference of the temperature with which they emit long-wave radiation versus the radiation that will come from lower levels. So if they rise to a higher layer, the temperature difference between their tops and the surface becomes larger, so they warm more. Green means there would be a cooling, so it seems to suggest that there's fewer of them, and then this could cancel, so there may be some hope. At the same time, what we are finding is the low clouds, the one that reflect sunlight, become fewer, less of them. So this means it's in heating. We can't reflect as much sunlight, we absorb even more. Something that's saving us a little bit here is that we convert ice clouds to liquid clouds if it's getting warmer. And the liquid cloud can reflect much more sunlight than an ice cloud. So you could have some hope that this negative effect here wins and this negative effect here. Unfortunately, that's not what has been found. IPCC concluded that the net effect of changes in clouds in response to global warming is to amplify it. So there's no help from the clouds. Okay, now let's go into radiation management. What is it that people think about when they discuss geoengineering or climate invention? Well, one of the things that we know from global warming is that whenever you have a massive volcanic eruption, it leads to a cooling. You have less solar radiation reaching the surface. So the first ideas that were put out there was to say, well, let's try to mimic a volcanic eruption, and so then we should be able to cool. So that's one aspect that I will go into. The second is here, we're coming back to the low clouds. Are we able to make the low clouds more reflective? While we also see something like that in the climate system, and that is when we see ships going over the ocean and making those clouds brighter. I'll come back to that. And the third possibility is to have fewer cirrus clouds, or put it differently, exaggerate getting rid of all the contrails and beyond. Okay, let's start with stratospheric aerosol injections. That's what this is called when you pump the aerosols into the stratosphere. As I said, it follows the analogon of a volcanic eruption. So if you have a massive volcano, so the last good one for the climate cooling was the Mount Pinatubo in 1991, where SO2, the gas SO2, was emitted all the way into the stratosphere, where it got oxidized to form sulfuric acid. And those sulfuric acid particles are the ones that reflect shortwave radiation, so that less comes to the surface, and this leads to a cooling. How large is this cooling? Well, you see this here. Here is a time series of temperature between 1990 and 2000. And here in 91, June 91 is when the Mount Pinatubo erupted. In the colored lines, you have different observations, and in the thin yellow lines, you have different climate model estimates. And there you see that all estimates, no matter if it's observation or climate models, agree that there is a significant cooling on the order of 0.3–0.4 degrees that you see. And it lasts a couple of years, after which when all the aerosol particles have sedimented and are removed from the stratosphere, then you reach the same temperatures that you have before. What this means in terms of stratospheric geoengineering, you can't just have one volcanic eruption and then wait 10 years and do the next, but you need to constantly inject particles to keep it cooling. the effect of which was already diagnosed in or studied in the 5th IPCC report, so almost 10 years ago, where they used climate model estimates. So here it's a schematic of the climate model simulation that were conducted. Gray is a business as usual scenario at the given starting point. You increase successively the amount of aerosols that you're injecting. Oh no, sorry. In gray is the business as usual, 1% increase in CO2 per year. So that's the normal business as usual scenario. In here, in yellow, you tune down the solar constant, so how much solar radiation reaches the surface, which is equivalent in injecting more and more and more aerosols into the stratosphere. And in this scenario, the assumption was, imagine that after 50 years, we have realized we don't want that, because if you have sulfate aerosols in the stratosphere, they destroy the ozone layer, and that has bad effects, and it has effect on the circulation and all that. So maybe at one point we say, we just don't want that. Then what happens is that you see that within a decade, you reach temperatures that you would have had in the business as usual case. So if we already now wonder if there are ecosystems that are not able to keep up with the observed rate of change, then this here becomes even amplified, and lots of ecosystems will have problems with this. Something else to consider if we discuss this is changes in precipitation. So as it's getting warmer, we also have more precipitation. Just because we are evaporating more water from the ocean, we have more water vapor in the atmosphere. If that condenses, comes back down, so you have more precipitation. If we inject more and more particles into the stratosphere, we end up with a decrease in precipitation. We understand this because here's this energy diagram again that I showed before. What happens at the surface? So we have half of the incoming solar radiation reaching the surface, where it gets absorbed and converted. It's only a third of which is re-emitted as long-wave radiation, half of which goes back to the atmosphere by latent heat, so that is evaporation. And so simply what you are seeing here is that you have less sunlight reaching the surface, there's less evaporation. And if there's less evaporation, then there's less precipitation. Because in the global annual mean, there is the balance between evaporation and precipitation. So the take-home message here is temperature and precipitation cannot be simultaneously restored if you use solar radiation management, so something like injecting aerosols in the stratosphere. Now you could argue that maybe that's not too bad, because then we don't have so much heavy precipitation, but the question is where it is, and I'll come back to that. But first of all, is there a limit to it? Can we continue? Will stratospheric aerosol injections, will this be able to solve our problem? Can we inject more and more and more and have much more of a cooling? This paper here says yes. The error here is at 8.5 watts per meter square. This is our business as usual scenario. So it says we can actually offset all the warming that we will be seeing by the year 2100 if we inject enough. But injecting enough means you need approximately 2/3 of all the sulfur emissions that we currently have. So that would be quite a bit. There's a different study, a newer study, that says, you can't even do that much. The most you can offset is 2 watts per meter square. 2 watts per meter square. In order to convert this in temperature, you can roughly divide it by 2. So you can only offset 1 degree of warming with stratospheric aerosol injection. And that's because the more particles you inject, the more they start to coagulate. the more they collide with each other, they become larger, and the larger they come, the sooner they become, the sooner they sediment out of the stratosphere. So there's the limit of that. It's self-limiting. The more you have, the more they coagulate, the easier faster they sediment, the sooner they are gone. So that's not helping us. Okay, and there is a rather new study that looked at, well, if you take climate models, so here is GeoMIP means model intercomparison project, where you have all the different climate models simulating some kind of geoengineering scenario. And here is their conversion of what they are saying, what a forcing and watt per meter square means in temperature. So the models are telling us approximately half of the watts per meter square is what we see in terms of warming. So if we offset 2 watts per meter square, this is a cooling of 1 degree. And now this new study looked carefully at all the volcanic data that we have and used that to see if the models are doing the right thing, and concluded, unfortunately, they don't. The cooling that you get per watt per meter square is around 20% less. Simply speaking, this means stratospheric aerosol injections are 20% less efficient than what we have just seen. So even less hope in that geoengineering helps us. Okay, here is a summary. What is stratospheric aerosol injections? What is it able to do? Well, it would block the sun, and that has positive and negative side effects. And you could also, for this geoengineering method, think about how you would do that. You would just take airplanes and release those particles. The positive side effects, yes, we have cooler temperature and more scattered light, which could be beneficial for forests to grow and other ecosystems, so that you remove some more CO2 from the atmosphere. And also crops then would have less heat stress, but it could be that if they don't have direct sunlight, but rather diffuse light, because the minute you have aerosols there, you have the diffuse light and not the direct light anymore. This could go in the wrong direction. And most important, one of the real problems is you're not curing the source of the problem. You're just curing the symptoms. So you still have CO2 that goes into the ocean, and you still have ocean acidification going on. I'm not going to read them, but there has been already 13 years ago a long list of all the benefits that we see. For instance, that we could reverse or reduce sea ice or ice sheet melting, sea level rise, and all that. But already at that point, look at the number, look at the sheer number of risk that they have come up. That's a factor 3 higher. So for instance, the ocean acidification I already mentioned, you will have impacts like the precipitation is not going to be equally changed, so there may be more droughts in Africa and Asia. Rapid warming will stop, we saw that. The moral problem, who will decide when to do geoengineering or not? Will you, if you get more precipitation in one country and take it away from another, what is that going to do? Will we actually continue to reduce CO2 once we enter such a technology? Lots of questions that need to be thought of. Going back to the science. Okay, we have seen the problems associated with stratospheric aerosol injections. Maybe there's something smarter. Maybe we just increase albedo. Here is the example of where we see that. Here is a sketch where you see a ship over the ocean. You see an unperturbed cloud that consists of very few cloud droplets. And here with all the ship exhaust, we form more and smaller cloud droplets. So overall, that leads to a larger overall surface. Like cutting an apple in four, you still have the same mass, but a larger surface. And the surface is which matters for the reflection of sunlight. And you see this here visually in the satellite image. People have been flying through that to understand the process in more detail. Here's an example of that. So if you look at the aerosol concentration in the background clouds, around 100 per cubic centimeter, in the track, factor of 10 higher. And then if you look at the cloud droplet number, how many cloud droplets does the cloud be consisting of? Then you see that you go from approximately 30 to 90. So it's a factor of 3. This means that not all the aerosols are needed to form the cloud, but if you offer the cloud more aerosol particles, also more cloud droplets will form. And so then on average, the cloud droplets are smaller. And if they are smaller, that together with having more of them increases their reflectivity. And that's what we saw in the satellite image. So which questions would be good for increasing the albedo of our low-lying clouds? If you look here at a sketch, how the reflectivity of the cloud depends on if we are in polluted areas or clean areas, then you see you have the highest impact if you go to very pristine areas, because there, this amount of generalized change in anthropogenic emissions has a huge effect on the cloud reflectivity. Where if you are in already polluted places and you add the same amount of emissions, it doesn't matter, the cloud doesn't become any brighter. So the regions that have been thought of would be really good are here what we call the marine stratocumulus decks off the coasts of the west coasts of Africa and America. And here you have normally the very dark ocean albedo, and you have clean air, marine clean air, and then the minute you have pollution plumes over that, that's where you see increases like this one. A rather new study looked at how much can this ship tracks, what we just saw, the pollution tracks from the ships, what kind of a forcing can that cause? And they looked at it in the South Atlantic and found that actually this forcing is rather large. It's 2 watts per meter square. So I told you before, divide that by 2 and you approximately get the cooling associated with that. This could be a cooling of 1 degree, so quite a bit. If the same is true not only in the South Atlantic, but globally. Also, climate models try to simulate that. Here is a number of climate models that were asked to make those marine clouds brighter. And what they found is actually on average, for a scenario where you have a warming of approximately 2 to 3 degrees by 2100, it's a cooling of around 1 degree. So it's not completely offsetting the warming that we are going to get, but it's a third or so less than what we would have had otherwise. And again, if after 20 years it would be decided to stop, then you would go back to temperatures that you had before. Okay, there's more albedos than just clouds. You can also put highly reflective material over all the deserts, or you can use crops that are brighter than others and see which effect that has. Sonja Seneviratne from my institute, she estimated that. And she exaggerated by saying, let's increase the albedo of all areas that are either highly populated, so that's as if you paint all the roofs white in a city, and agricultural areas. Just increase the albedo there by 10% and see what it does. And then you see you get a substantial cooling. So the average temperature in those areas is reduced by 0.7 degrees. And more importantly, the maximum temperature is reduced considerably. So you have less heat stress in the cities. So this could be really interesting. The only problem is if you paint roofs white or something like that, you have to ensure that they remain white, because otherwise the effect is lost. Okay. Here is a study that compared all of that, what you can do. So if you have for reference CO2 doubling, approximately 3 degrees warmer, and if you make also, if you paint all the roofs white, yes, you would get a cooling similar to what Sonja has estimated, a little less, 0.5. If you take brighter crops, a little higher cooling. Marine clouds is what we have seen, is somewhere there in the middle. Most effective would be to either put some reflective material in the deserts or to put sunshade somewhere in space. That's technologically the most complicated, but would be from a radiation point of view be the most effective. And this followed by the reflective material in deserts. We can look at the pro and cons of this. While the potential in cities is low because there are not so many roofs if you compare this over the whole area of the globe, to medium from the ocean, the clouds, and the deserts. It is only efficient if the bright areas remain clean and bright. And the costs are most expensive if it comes to desert and cities, and of course space technology. They are cheaper when it comes to clouds because that just requires some injection of aerosols. What will be tried though, and that was recently in Nature, that if you can do it over a targeted region, for instance, to locally save coral reefs, because coral reefs are already now suffering from the heat stress. So maybe something like this is beneficial locally. Okay, with this I come to the last. Decreasing cirrus clouds. Would this work? Could we actually get rid of all the cirrus clouds, and would this help us? Well, what would it do? If you, cirrus clouds on average, if you calculate it, warm the climate by 5 watts per meter square. So you see here a global distribution of that. 5 watts per meter square is more than the CO2 doubling. So yes, if we are able to get rid of all the cirrus clouds, there we go. Then we have cancelled the CO2 doubling. But how would we achieve something like that? This sounds like science fiction, right? Getting rid of all the clouds. Well, the idea behind it is that if you look at the sky and you have the normal cirrus clouds unperturbed by anthropogenic activity, it often is formed from sulfuric acid particles that are high in the atmosphere. And so you have the cloud consisting on very many small ice crystals, and they do reflect some radiation, but more importantly, they absorb the long-wave radiation that's being emitted from lower levels and emit that at their own colder temperatures. But the idea with cirrus seeding is that you inject some aerosol particles that will help ice crystals to form. It will help ice crystals to form at lower altitudes, at warmer temperatures. Because if that would be the case, then those ice crystals would grow larger. And if they grow larger, then they would sediment faster. And so then they would dissolve the cirrus cloud and also remove water vapor with that. And this would be highly beneficial because then the cloud becomes optically thinner. So it's the opposite from a ship track. Exactly the opposite. Now we are going from a cloud with very many crystals to a few, and then more long-wave radiation goes out to space, and this cools. Does it work? Well, again, we have to rely on climate model estimates. There have been a few. It started 8 years ago, where this was more made popular. And you see here watts per meter square, and you see the number of ice nucleating particles. So those are aerosols on which ice crystals can form. And what you see is that there is cooling. There is a cooling of 2 watts per meter square for a concentration of around 20% per ice nucleating particles per liter. So this is good. This is what you want, or what one would want, because this would have to make the cirrus clouds thinner, and this is the result of it. And what you're seeing here at the end, if there's too many ice nucleating particles, then what happens from here on is similar to the ship track. So we're adding particles and particles and particles. And so the cloud becomes thicker, and the cirrus cloud that becomes thicker means it traps more long-wave radiation. So yes, one study found there's optimal seeding concentration, but there is the danger of overseeding, so going exactly in the wrong direction and ending up with a positive effect that we clearly don't want. And the other thing that you also see is that there is a lot of discrepancy. I'm going to skip the details of what we have been doing next in the interest of time. Just go to the updated, no, one more. Go here. To show you some more of the uncertainties associated with that. There's 2 climate models that are estimating the effect of cirrus thinning. One is ours here, and one is the American one. If you look at what they simulate for warming, if you had 1.5 times the present CO2 concentrations, our model says 1.8 degrees, the other model says 2 degrees. So this is roughly speaking similar. This model, if you apply cirrus seeding, says the global mean warming is reduced to 1/3. And there are actually areas in which we see a cooling if we are able to make the cirrus cloud thinner and remove that. So here you see it's pretty much everywhere a cooling that you get with a lower temperature of 1.4. So this would argue to further look into cirrus thinning. Our model says something else. Our model says, it's 1/3. It's 1/3 of the warming that you can remove. And so the overall cooling that we have is much weaker. It's only 0.5. It's only 1/3 of what we see. So this tells you that there is still lots of discrepancies or lots of uncertainties between different models. And that has to do with how cirrus models are treated in the model, how the aerosols are injected, and all of that. So I've said that. So to come to an end, can we think of a smart way of then combining different climate invention methods? Or also, if we compare this, do we have a means to say which one is better, which one is worse, or do we piece them together? What is the smart way of doing it? Here, in this paper, they tried to combine it. And what they looked at here, so just look here, stratospheric aerosol injection. If this is the global temperature, imagine we had abruptly quadrupled CO2. We are here. We have a 12% increase in precipitation, 6.5 degree increase in temperature, and we want to get rid of that. So either you can get off this temperature increase by injecting 44 teragram sulfate into the stratosphere, but what we have seen, we cannot reduce temperature and precipitation at the same time. If we reduce all the full amount of temperature, then we have less precipitation. If we just do cirrus cloud thinning, and they did it by changing the fall speeds of the ice crystals, So imagine, so take this as a proxy for cirrus cloud thinning, then you see the changes are much more modest. You don't even reach temperatures that you had before, but also the decrease in precipitation is much more modest. So they are then thinking of to combine it in a way that you take here, say, if you wanted to restore global mean precipitation and global mean temperature at the same time, you take X% of stratospheric aerosol injection and some percentage of cirrus cloud thinning to achieve it. Or you do that for over land. If you just want to restore land precipitation, then you can do that in a different way. The latest IPCC report is also comparing the temperature changes and precipitation changes to evaluate if there is areas on the globe where you do not reverse the temperature or do not reverse the precipitation. And if you have those vertical stripes, this argues for low model agreement. So no matter what we are doing, if so CO2 reduction is just the inverse from CO2 doubling, just to be looking at this on the same color scale, the models don't even know how precipitation responds to a change in CO2. And also then, of course, they don't know how the models respond to if you reduce solar radiation or stratospheric sulfate aerosols or have this marine cloud brightening. What may be of interest is to zoom in here at the Indian summer monsoon. This is one of the bad side effects, negative side effects of marine cloud brightening. If you are doing that, then you increase the Indian summer monsoon. And that already now leads to huge floodings. For stratospheric aerosol injection, it goes the opposite way, then you have a reduction in the Indian monsoon. So locally, there are some changes happening. Temperature overall looks rather similar in all the methods that are being tried out in the models. You have the largest cooling at the poles, exactly where you otherwise have the largest warming. This is my last slide. People have been trying to characterize the different climate engineering methods, with the idea behind if you have an effective method and an affordable method. So an affordable method means it's cheap. So if you had a perfect geoengineering method, it would be really effective, so it would get rid of all the warming that you want, and it would also be cheap. The worst geoengineering method would be one that's not effective and expensive, so definitely nothing that we want. Of the three things that I've shown you, stratospheric aerosols is shown to be rather effective. We have seen that. Depending on which model you look at, you can cool quite a bit, but it's more expensive than if we are changing the clouds here. This is not the whole story, because what we also need to consider are side effects, safety. Stratospheric aerosols are not the best in that effect, because we know that they continue to harm the ozone layer, and that will have effects on the UV light that comes through. Marine clouds also not, because I just showed you that it leads to an increase in the Indian summer monsoon. So cirrus clouds would probably be the best, because they also act upon the long wave radiation, so the same as the greenhouse gases, and so have most similarity to what we have been doing. But of course, also for those, ocean acidification will continue. And these are all the other methods that I didn't discuss. What you see from that is there's nothing that's here. And with this, I'd like to conclude. Cloud aerosol interactions remain the largest uncertainty in terms of radiative forcing since pre-industrial times and today, and how clouds respond to future warming is also the least understood from all the feedbacks that we have. The climate invention methods that I discussed none of them cures the problem. All of them just cover the symptoms. And ocean acidification continues. So far, there's no single method that can get rid of all the warming. So we have seen that they can compensate only part of it, and that the negative side effects seem to dominate. So in short, there's nothing that works except vigorously reducing greenhouse gas emissions, much beyond what is currently done. And with this, I'd like to thank you for your attention.
If there are any questions, please ask. Now's the time for. If not, I'm going. Yeah, we have one question.
So the question was, what do you think how the carbon industry will react on outcomes of the geoengineering? Will they act that they don't reduce the carbon emissions anymore because they see any chance that it will help? So I think more or less this was the question. Did you understand?
Yes, 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 of course. It would be the easiest for everybody. Then we wouldn't have to change our lifestyle. We could continue as business as usual pretty much and have the technology that keeps the warming in a bearable level. But I think it's changing, especially now with energy prices going up and all the industry is looking to make profit. And it's clear by now that profit is not be made if you waste energy. So the energy to become more energy efficient is also something that all the industry is after. But of course, they would love it if there is some technology so that they can continue to sell all their energy intensive products, for sure.
Thank you. Any other questions?
The question was, when we start with the injection of the aerosols and we stop for any reason, and then it's getting up to the normal temperature again. And I think the question was why we should stop to do the injection and why it's going up again. Was this the question? And why the specific time period was chosen in the model? Was this just like for any reason?
The specific time period was just a scenario. Say we do that for 50 years, and imagine what we have seen, for instance, from the marine cloud brightening, that you have an increase in the Indian summer monsoon. And then we say, well, this is unbearable. We don't want this increase in the Indian summer monsoon. Let's stop. That would be a reason for stopping.
Okay. They want to lean. Okay. They want to lean on another question. If we are stopping to inject the aerosols, in another slide you showed before that some the trees or the corporate or and so on, they want to profit from them, so they are growing faster or they can grow better. Can they make some effect on the temperature or in the reduction on CO2? What is valuable or not?
Yes, that's actually, it is discussed in the latest IPCC report that there is some hope that yes, if you have a hazier sky and have more diffuse radiation instead of direct radiation, and there is added growth or benefit, some plants like to, they grow better if it's diffuse radiation. And if they grow better, then they would reduce more CO2 from the atmosphere, and that would help. But it helps only to a tiny bit. It won't save us with the CO2 problem. We won't get so much out of the atmosphere to be able to rely on this methodology. But it's looked at as a small side effect, a small positive side effect.
Okay. Theoretically spoken, if there is there a chance that when we would say theoretically that we grow in all the America, North and South America, enough plants, or we took all plants there or trees, and we also would do growing algae plantations in the sea, can we reduce the CO2 emission from the humans? Is there any chance, or is there not enough space to grow all the plants?
There's not enough space. There's just, simply speaking, not enough space, because you also need the space for agricultural activities, right? So you can't put trees everywhere. There is a maximum as to how many trees you can be doing. Actually, I'm not sure how I can get out of my presentation mode without leaving this thing, but I can continue here. There is a slide that looks actually at that here. It's in German, but I think you can read that nevertheless. If you compare, there is something called bioenergy, carbon sequestration, and carbon sequestration afterwards, and it compares the different scenarios that you need. So there is here enhanced weathering, afforestation, that's what you were just asking, can we just plant trees everywhere? How much energy is needed? And then color-coded the land requirement that comes along with that. And you see, for instance, here for the afforestation, it is very appealing. You don't need any energy for that, and you definitely draw down, you get negative emissions, so you really get the CO2 out of the atmosphere, but it's huge amounts of land that you need for this. Mind you, there's also here, there's nothing that solves the problem completely, because this is called direct air capture, so directly getting the CO2 out of the atmosphere, then you don't need any land requirements, so that makes it really attractive. And you also have negative emissions, that's also great, but it requires lots of energy, so it's also not a winner. And here, bioenergy and carbon capture and storage means that for one, and also it looks like how much water you need, the amount of water that you need here. It's not too bad in terms of land requirement, but it still is some land requirement. So it's not as much land as if you put trees everywhere. So this goes in a direction that's a little bit better, but then there's the trade-off, like, do you put food? Do you use the agricultural areas for food or for producing bioenergy?
Okay. There are other questions in the audience? And if we would use the sea for algae, for plantations for algae or something like that, I think in the sea there are more space than on land.
Yes, so what has been looked at for the ocean, that's shown here. This is a comparison of afforestation that we just discussed, and putting, if you put, actually not growing algae. I mean, it has been looked at what's called the edges of the ocean, where you do have plant growth. You can do a little bit, but if you do that, then you are limited to just the ocean edges, and there's just not a lot of space. What has been proposed is to put lime to the ocean, and then when you do that, then afterwards you are able to absorb more CO2 again. So here, this is the change in temperature that you are seeing, and this is how much CO2 you are getting out of the atmosphere. And you are seeing that, yes, a little bit works. So you can either do that by adding lime or by putting iron. And if you add iron to the ocean, that's like phytoplankton is often limited by the micronutrient iron. So if you add iron, then the phytoplankton grows better, and it takes CO2 out of the atmosphere. But you see that the global numbers here are not a lot. It's a little bit, it's not even 0.3 degrees centigrade in the global annual mean that one is able to reduce the warming. So it also doesn't seem to be the method, the golden recipe.
Okay, thank you.
Yeah, so thank you also from my side. You had an interesting slide about the effect of the albedo. It was distinguished between the albedo of agricultural land as well as rural parts. And there was some effect on albedo of the rural parts of cities, which is on brighter colors of the roofs and so on. And this is not a big effect, but a positive effect. And it has a side effect, which is also positive. It's the heat island effect within the rural areas is lower than. So it really helps. And it also helps for reducing the emissions for cooling. So we have less energy for cooling. So we emit less CO2 for producing the energy for the cooling. So it's a double win-win situation. It's not very big, but we should think about, especially for the architects and for the planning people here. I think it helps. What's your estimate of the percentage it could help in practical reasons? So what we really can do for this?
I have no clue how practical it is. I know from Sonja Seneviratne's study that this scenario that she did, a 10% increase in albedo, this is huge. This is more like an upper bound of what you can get. She had also more realistic examples, but then you see less of an effect. But I completely agree. What you're seeing here is exactly getting rid of the heat island effect. That's exactly what you are after. And you see this really clearly, because this is the maximum temperature, and that you reduce that, and you reduce that to a substantial degree. So yes, I fully agree. I think there's less. With that, you can't do any harm. It's already paved over areas. If you, whatever you make white or have plants there for cooling through evapotranspiration, all of that is of course good.
And with all the methods you mentioned, you always talked about the risks and about the unknown. So you talked about the models which can forecast it somehow, but not perfectly, and there is some risk in unknown. It's an experiment on Earth. We never did it before, and we don't know how it will end up. Most or even all of your methods were unknown things which will happen in future. But some are not. So one experiment is the albedo, because we reduce it, so we come back to history and not to future. And the other thing is to take out CO2 from the atmosphere. So we go back to history, and so we know what was in history, so we can rely on. So taking out CO2 out of the atmosphere could help without any risk. But what's your estimation? Is it feasible? Is it feasible in terms of cost and in terms of time schedule? It takes a lot of time to develop all these methods, and it's high cost. Or what's your estimation about this?
Yes, I mean, it's done in small bits, right? It is already that where you extract oil and gas, then you pump CO2 back in. So some of that is being tried on a small scale. The real problem is none of that is scalable. You can't scale it up too highly, because where do you want to store it? I mean, with in Switzerland, Basel had a small earthquake when it was trying to get out geothermal energy, and something like that. If you do put CO2 in, you also change what's going on there. You change the pressure underground, and that's just not without any side effects. So there is not, I mean, had we found where you can safely put CO2 into the, back into the soil below the earth, it would be done. Iceland has done quite a bit, but Iceland can withdraw CO2 from the atmosphere rather readily, because they have so much natural renewable energies that they can do it. And I think there are also on Iceland, you also try to put CO2 underground. So there are small plants or places where that is being tried, but not on a large scale, not what's needed to solve the CO2 problem.
Yes, I also heard there are experiments at Iceland in a small scale, and yeah, and it takes a lot of time to upscale it, time and money. That's really high expensive. So if you count on the costs per saved CO2 or avoided CO2 or sequestered CO2, it's several hundred euros per ton. And yeah, to reduce emissions is much cheaper, or if even profitable. That's the other way around. So we should start with this, I think. Yeah.
Oh yeah, definitely, because also the geomorphology in Iceland is very different from most of the other places. So you can't even, it's not alone in upscaling in terms of area, but I think what they have, I'm not a geologist, so I don't know exactly what they have, if they have basalt or granite, but they have one thing that's very good, but we don't have it in so many other places elsewhere. That also limits the upscale, how much you can upscale it by.
Other question?
We have a question on the audience.
From how geoengineering technology will
The question was from now in the future, in 10 years, which geoengineering technical method we can is ready to use? Is there any, or is there they're not,
Well,
not really?
Switching to like what you can do and which will help, and I'm not sure if you would call that geoengineering. If you, for instance, after harvesting, you leave the freshly cut straw on the soil, then you make the soil brighter, and that has some cooling, and this has a higher albedo. And this goes in a similar direction than trying to change to brighter crops. This is something that can be done immediately, and that has benefits throughout. But in terms of if we really have to do something, the only thing that you can do quickly is to change in cities the color of the roofs, or that you have green on the rooftop or something like that. That's the only thing that can be done quickly. For stratospheric aerosol injection or marine cloud brightening, the big question is who should decide about whether something is done or not. Because if you do it on a small scale, then you won't see a global effect. If you do it on a small scale, there's no harm, but it's also no benefit. And if you want to do it on a large scale, then you need all the countries to agree. And that's pretty tough. I mean, there was also the idea, for instance, if you should have regional climate intervention to save, say, the Arctic sea ice, but there all the economic interests are they want to have a free Arctic Ocean, because then you can have much better ship routes and oil and gas exploration. So if the countries around the Arctic are not agreeing with climate engineering, who will tell them that it needs to be done?
But your answer leads to another question. Is there any I don't know, politician leaders, the UN, the EU, or somebody who think about to say, yes, we are going to do some geoengineering, the aerosol injection, for example, if we want to step over the 1.5 degree. Is there any push, or is there any persons or groups of persons they think about that, or is this just a scientist theoretical knowing and discussion right now?
It still is a scientific discussion, but I think it will be discussed more and more the closer we come to the 1.5 degree global warming. So far, it's not being taken up. I think it's still the hope. For one, it's still too far away from politicians. It's not yet in their terms of serving periods. And yeah, but I think it can be ignored for too long, because then you either have to face that, yes, now we really have a problem with temperature increase or global change, or we do something.
Of course. Okay. Is there another question?
Oh.
I have there just one last question, I think. In one of your very first slides, you have shown how the temperature is effects on the several areas, and there you have shown that on the poles effects more the 1 degree than in other areas. Is this because on the poles the 1 degree is just an average on the whole globe? And is this because on the poles the warming is much more than the 1 degree? It's about the double or the third? Or is this because it's so sensitive, these areas?
You mean something like this, right? Not really this, but a similar graph
No,
like
I think
that.
it was the third or the fourth slide from the IPCC report, the diagrams with from white to violet.
I didn't show it.
Yeah, and stop this one. A bit up. Yeah, this one. I think. Yeah, and there's the first one.
Warm water corals.
Was warm water, and Arctic region is the first.
Yeah.
Yeah, and
Yeah. So what was your question then?
Why effects that much on the Arctic regions? Because if you think about it, the Arctic regions is normally -10, -20. In the Antarctic, it's -40 degrees, and if they're 5 degrees plus, so it's like 35, -35 degrees, it shouldn't affect that much on the poles. Why affect that much?
The effects are higher at the
Yeah,
poles. It's now in mid latitudes over land, so the land warms faster than the ocean. That's one thing, and also high latitudes warm more than the tropics. And that is because like most of the sun reaches the tropics, and there is heat transport to the poles, and so you have like it's called Arctic amplification. So for 1 degree warming that you have worldwide, in our latitudes, mid latitudes continents, it's already twice that. So the Arctic is around 3 times this. So you have the highest warming there. So they experience a much faster temperature increase than you experience elsewhere. And then it's a question of like how the fauna and flora is able to cope with that. I mean, that's where you see the pictures, right, of ice bears not finding an ice sheet or to be on. Just because the ice becomes thinner, and the wildlife is completely changing. They do require sometimes that you do have sea ice and not ice-free ocean.
Okay, so could we say that in the poles or in the Arctic, it's right now they have 3 degrees warming in average, or is there any or is there no temperature what we can say right now? Because like we said, here in the Alps, I think we have already 2 degrees, right?
Yeah, now I need to look back into this. When you look here into this figure, and now I need to be able to, to finally understand your software there, I think. Share here. Here, if you look at this is, I mean, this is the opposite. So you can invert it and look at the warming. So this is the degree global cooling for a global uniform 1 degree. And so if you turn it around, it's the warming that you get for globally uniform 1 degree. And then you see here in the Arctic, it's more than 2.5 times this.
But it affects more in the Arctic than in the Antarctic, right?
Yes.
It affects more in the north than the south.
Yes, and that's because of the way the heat transport is to the Arctic. To the Arctic, the heat transport is from the ocean, so you have the warm Gulf Stream that brings the water up there, Whereas what happens around Antarctica, you have a circulation that's really zonal. So you don't have so much of the mixing between the tropical, both actually in the atmosphere and in the ocean. You shelter it much more. The Antarctic Peninsula is much more sheltered from what happens in the tropics than the Arctic is.
Okay, thank you very much. Is there any other questions in the chat? Thank you very much for your time, for the really informational presentation and for the discussion.
Yeah, also thank you from my side, and thank you for listening, the audience. Thank you very much, and have a nice weekend. And yeah, goodbye, have a nice time. Bye.
Thank you very much.
Thank you.
Thank you. It was my pleasure.